Hello everyone, in this video we are going to talk about the at-rest lateral earth pressure. So in this video we will see together how we can calculate these lateral pressures on retaining structures or on underground structures. So first of all, let's talk about the different types of lateral earth pressure. Actually, we have three main categories or three main types of lateral earth pressure. The first one is at rest lateral earth pressure, at rest lateral earth pressure, and the second type it's active lateral earth pressure, and the third type it's passive lateral earth pressure. So in this video we are going to focus on the first type only. We are going to talk about the at-rest lateral earth pressure. So in order to define this type of lateral earth pressure, we have to assume that or imagine that we have a retaining wall or some underground structures, any underground structure which is embedded completely in the soil like this one. So in this case, this retaining wall, it's not motivated to move in any direction. It's not forced to move to the left direction or to the right direction. So the retaining wall will remain at rest. It will be positioned or it will be forced to remain in its position. It's not forced to move to the right direction or to the left direction. Here we have a surcharge load, maybe 10 or 20 kilopascal. It doesn't matter here. So in this case, if you would like to calculate the lateral earth pressure on this retaining wall, this pressure will be calculated using the equations of at-rest earth pressure. And of course, there will be earth pressure on both sides of the retaining wall, and they will be equal in magnitude but opposite in direction, so that the retaining wall will remain in an equilibrium state. So to summarize what we have just said, the earth pressure at rest, there is no wall rotation, there is no wall movement, the wall remains in its position without moving in any direction. In this case, if you would like to calculate the earth pressure, the lateral earth pressure on the wall, you use this equation, sigma O, or it's sigma O, it's equal to KO sigma V. So you have to first calculate the effective vertical stress. This is the effective vertical stress, which is a summation of gamma h. And you have to calculate this value. You have to calculate this value. Then you will multiply this value by a coefficient which is called the lateral earth pressure coefficient, or here we can call it the coefficient of lateral earth pressure at rest. So for this case, the coefficient, which is KO, we have two equations. In the case of normally consolidated clay and granular soils, sands and gravels, you will use this formula. So KO, it's equal to 1 minus sine phi. So if you have the value of phi, you will substitute in this formula and get the value of KO. For the case of over-consolidated clays, in which the over-consolidation ratio is greater than 1, you have to use this formula, which is KO equal to 1 minus sine phi by the square root of over-consolidation ratio. So if you have an over-consolidated clay with an over-consolidation ratio which is greater than 1, and you use the value of OCR and substitute in this formula, for clay you have the value of phi, it's equal to 0. Pure clay doesn't have any value of phi, internal friction angle, so the value of phi is equal to 0. So when you substitute in this relationship, you have 1 minus sine 0 by the square root of the over-consolidation ratio. Let's assume that the over-consolidation ratio it's 1.5. So for these cases, you will see that KO generally will be greater than 1. So for over-consolidated clays, you can see that in some cases you will have KO it's greater than 1. So when you compute the value of lateral earth pressure sigma O, it's KO by sigma V. So KO it's greater than 1. This will lead accordingly to the fact that sigma O or sigma horizontal will be greater than sigma V. So in some cases you can observe that by calculations that the lateral earth pressure is greater than the vertical stress. However, in granular soils or normally consolidated clay, if you have maybe a sand layer, and for this sand the value of phi it's equal to 30 degree, so you have a KO value which is 1 minus sine 30, you will have a KO value of half. So if you calculate the lateral earth pressure at rest, you will find that sigma horizontal is equal to half by sigma V. So you will find that at any depth under the ground surface, the lateral earth pressure will be less than the vertical stress. So generally, you can't assume that the lateral earth pressure will be always less than the vertical stresses, or vice versa. You have to calculate the lateral earth pressure coefficient, which is KO. So for some cases, or for over-consolidated clay, KO may be greater than 1, and therefore the lateral earth pressure will be greater than the vertical stresses at a certain depth under the ground surface. However, for some other cases, such as for sands or gravels, you will have the lateral earth pressure lower than the vertical stresses at a certain depth. So anyway, let's talk about our example. This example, it's an embedded tunnel. It's an underground structure. So you have your cross section, and you are required to sketch and label the values of the lateral earth pressure on the final shape of that tunnel. So this is your final shape, and this is a cross section of your tunnel. You have here the ground surface, and 2 meters below you have your groundwater table, and 3 meters below there is a line between two different soils. You have here silty sand with phi 28 degree, and here you have middle sand layer with phi of 32 degrees. So you have two sand layers, but for the upper 5 meters, this 5 meter layer, you have phi equal 28 degree, and for this 5 meter layer you have another sand layer with a different phi angle, which is 32 degree. You have here, this is 5 meter. Take the unit weight of the soil, 20 kilonewton per meter cube. So this is the saturated unit weight of the soil for the problem under investigation. So before we begin our calculations, let's talk about the points at which you will calculate your lateral earth pressure. So where to calculate your lateral earth pressure? This is very important to predetermine the locations at which you have to calculate your lateral earth pressure, so that you can sketch and label your diagrams. So the first point, it's the uppermost point of your retaining wall of your underground structure. So when you deal with a tunnel like this, you have to calculate at this point, the uppermost point in the underground structure. You will compute the lateral earth pressure on it. The second point, it's the lowermost point, so you will have to calculate here in the lowermost point on the retaining structure. Then add the groundwater level. So if you have a groundwater level, you will compute the lateral earth pressure at its location. Actually, here in this problem, or in this case, we have the groundwater level at the same level of the uppermost point. So here, this is your point in terms of it represents the uppermost point, and in the same time it represents the location of the groundwater table. So this point you must calculate the lateral earth pressure at it. And finally, when you have an elevation between two different soil layers, you have to calculate at this elevation 2 times, one on the top of this elevation and one at the bottom. So if you have your elevation here, this elevation, this line, it's between two different soil layers. So you have an upper sand layer which has a phi of 28 degree, and downwards you have another sand layer with a phi of 32 degree. So this line, it's an elevation between two different soil layers. So when you have an elevation like this, you have to calculate 2 times, one on the top of the elevation, or one on the top of it, and one of the bottom of it. One here and one here, one just on the top and one just below the elevation. So here in our example here, you have 4 points. This is point number 1 on the uppermost or at the groundwater table. It represents both of them. And at this elevation, which lies between two different soil layers, you have 2 points. Point number 2 just on the top of it, and point number 3 just below this line, and the final point, which is your downmost or lowermost point of your retaining structure or of your underground structure, which will be point 4. So you have here 4 points. You have to calculate your lateral earth pressure 4 times. So let's begin with the calculations. So first of all, we have to calculate the coefficients. Just use this formula, which is 1 minus sine phi. You don't have any information here saying that you have any over consolidated clay, so you will use this formula. So KO, or K at rest, the coefficient of lateral earth pressure at rest, it's 1 minus sine phi. But you have here 2 soil layers. The first one, or the upper soil layer, has a phi of 28 degree. So you have to calculate or substitute with a value of 28 degree. 1 minus sine 28 will be 0.5305. And for the second soil layer, the bottom layer, which is middle sand with a phi of 32 degree, you have a KO for the second or for the lower soil layer, 1 minus sine 32, and it will be equal to 0.47. So for our problem, again, we have here for the upper soil layer a KO value of 0.5305, and for the lower soil layer you have a KO value of 0.47. So let's begin our calculations. For the first point, which is the uppermost point of your underground structure, you have to calculate the lateral earth pressure coefficient, and then you will have to calculate the stress. So the stress E, or sigma, it will be gamma H by KO. So for the point number 1, E1, you will have to compute the vertical stresses, effective vertical stresses, which is actually here, it's the stresses due to the own weight of the soil above this point. So the own weight of the soil above this point, it's gamma H. It's gamma of the soil. You are above the groundwater table. As long as you are above the groundwater table, you will use gamma saturated, and as long as you are below the groundwater table, you will use gamma submerged, because you are calculating effective vertical stresses. So if you are above the groundwater table, you will use gamma saturated. If you are below the groundwater table, you will use gamma submerged. So for point 1, the on weight of the soil here, it's above the groundwater table, you will use gamma saturated, which is 20 kilonewton per meter cube. H, the depth of the soil is 2 meter, and Ko here, this point number 1, it lies within the silty sand, the upper soil layer, which has a value of 0.5305. So you will have here, it's E1 20 by 2 by 0.5305. You will have E1 21.2 kilonewton per meter square. For point 2, you have here your elevation, which lies between two different soil layers. So point 2, just on the top of this elevation, it's here. This is point 2. So for point 2, it's gamma H Ko. Gamma H, it's the on weight of the soil above this point. So this this effective vertical stress can be divided to two parts. The upper part, it will be 20 by 2 meter gamma H, gamma saturated 20 by 2. However, below the groundwater table, you will use the gamma submerged. So instead of 20, we'll use 10, which is gamma submerged of the soil by 3 meter. So gamma H here will be 20 by 2 plus 10 by 3. And then Ko, which is the coefficient of the upper soil layer. Just keep in mind that your point, which is point 2, it's on the top of this elevation, so it lies within the upper soil layer, which has a phi of 28 degree. So you will use Ko1, which is 0.5305, Ko value for the upper soil layer. This will give you a lateral earth pressure of 37.1 kilonewton per meter square. For point number 3, again, this is the elevation which lies between two different soil layers, and point number 3 was just below it. So for point number 3, again, you have this on weight of soil. This will represent the value of gamma H, or the effective vertical stress. So for point number 3, gamma H by Ko, gamma H, again, just like point number 2, gamma H will be 20 by 2 plus 10, which is the gamma submerged by 3. And this term is the same term we have already used with the point number 2. So here in point number 2 and point number 3, you will observe that you have the same effective vertical stress, 20 by 2 plus 10 by 3. However, point number 3 lies within the bottom soil layer. So you will import in your calculations the Ko value of the bottom soil layer corresponding to a phi of 32 degree. So here you will multiply the value of the effective vertical stress by Ko2, which is 4.47. So to summarize, the difference between E2 and E3, the difference between these 2 points, they have the same effective vertical stress, but they have different values of Ko, because the point number 2, it lies within the top soil layer. However, the point number 3 lies within the bottom soil layer. So E2 takes the value of Ko of the upper soil layer, which is 0.5305, and point number 3 will take the Ko value of the bottom soil layer, which is 0.47. So you will find that your lateral earth pressure is 32.9 kilonewton per meter square. The final point, which is an easy one, this point, the lowermost point of your underground structure, E4. So you have the value of effective vertical stress. It will be the on weight of the soil up on the top of this point. So you have here this part, it's 20 by 2, and then you have this part, it's 8 meter deep, and it has a submerged unit weight of soil of 10 kilonewton per meter cube, so it's 10 by 8 meter. So for point number 4, the effective vertical stress will be 20 by 2 plus 10 by 8. And for point number 4 lies within the bottom soil layer, which is middle sand, and it has a KO value of 0.47. So you will multiply this term by 0.47. So E4, where you will find that it's equal to 56.4 kilonewton per meter square. At the very end, you have to calculate the water pressure. You have a groundwater table, so don't forget that you have some lateral water pressure on your retaining wall or on your underground structure. The water pressure is very easy to calculate. The water pressure, it's gamma water by H water. Just E water, it will be equal to gamma water by H water. So if you have here a datum, you will use this datum to calculate and draw the water pressure. At the groundwater level, you have a water pressure of 0. However, at the lowermost point of your structure here, you will have a water pressure which is equal to gamma water by H water. So the value of H water is the depth of the point below the groundwater level. So you have here, this is the depth, 8 meter. So H water, it's 8 meter, and gamma water, it's the unit weight of water, which is 10 kilonewton by meter cube. So you have here 80 kilopascal or kilonewton per meter square. So this value is it's equal to 80, and you will draw a line between the uppermost point here and the lowermost point here. So this value, it's equal to 80 kilopascal, and this value it's equal to 0, and this is your water pressure on your underground structure. So this is the final shape of the lateral earth pressures on your structure. You will find that at the uppermost point of your underground structure, you have E1 of 21.22 kilopascal. Then at point number 2, it's here. This is point number 2, this is point number 3, this is point number 4, and this of course was point number 1. So for point number 2, you have a lateral earth pressure of 37.1. So you are increasing linearly from 21.22 to 37.1, a linear increase. Then at the same elevation, there will be a drop from 37.1 to 32.9. So at the same elevation, you will have a drop from 37.1 to 32.9. Then finally, at the lowermost point of your retaining structure, which is point number 4, you have a lateral earth pressure of 56.4. So you will come from 32.9 to 56.4, a linear increase until you reach the lowermost point of your underground structure. This is for your lateral earth pressure at rest. For the water pressure, as I have just said, you have a water pressure of 0 here, because this represents the groundwater level, and at the lowermost point of your structure, this is 8 meter deep, so you have water pressure of 8 meter by gamma water, which is 10, and therefore you have a value of 80 kilopascal. So generally water pressures are in the shape of triangular pressures. However, the shape of lateral earth pressure can take different shapes like this. It can be a triangle, it can be rectangle, it can be trapezoidal. It depends on your application.